Welcome to an experiment that goes beyond surface-level gardening advice and dives deep into the microscopic world that makes or breaks your soil health. The question before us is deceptively simple yet profound. Does cooked rice or raw rice create a more powerful microbial explosion when added to compost tea? This isn't just about tossing ingredients into water and hoping for the best. This is about understanding how different carbon sources feed specific communities of bacteria and fungi, and how those communities transform into the living fertilizer your plants crave. Compost tea has earned its reputation as liquid gold among gardeners who understand that healthy soil begins with thriving microbial populations. When we brew compost tea, we're creating an environment where beneficial bacteria, fungi, protozoa, and nematodes can multiply exponentially. These organisms break down organic matter, make nutrients available to plant roots, suppress disease-causing pathogens, and improve soil structure. The difference between mediocre compost tea and exceptional compost tea often comes down to the food source you provide these microorganisms during the brewing process. Carbohydrate-rich additives like rice serve as, rocket fuel for microbial reproduction, but not all carbohydrates are created equal in the eyes of soil biology. Today we're examining two forms of the same grain to determine which unleashes superior microbial activity. Raw rice contains complex starches locked within intact cell walls, requiring specific enzymatic action to break down. Cooked rice, however, has undergone gelatinization, a process where heat and water break down starch molecules into simpler, more accessible forms. This fundamental difference in molecular structure should theoretically attract and support different microbial communities, and our experiment will reveal whether theory translates into observable, practical results for your garden. Alright, let's get ready to brew what I like to call the microbial battleground. Creating a fair comparison demands, some real precision in methodology. Both batches start off with exactly the same base ingredients. That's 5 gallons of dechlorinated water, 2 cups of high-quality finished compost, and 1/4 cup of unsulfured molasses. The compost, provides the initial microbial inoculum, while molasses supplies those simple sugars that feed bacterial populations during the early stages of fermentation. Each batch receives continuous aeration through aquarium pumps fitted with air stones, ensuring adequate oxygen levels to support aerobic decomposition rather than the foul-smelling anaerobic processes that harm rather than help your soil. The rice additions require careful preparation to maintain experimental integrity. For the raw rice treatment, we measure exactly 1 cup of uncooked white rice, which gets added directly to the brewing tea without any pre-treatment. The cooked rice treatment receives 1 cup of white rice that has been boiled in 2 cups of water until fully cooked, then cooled to room temperature before addition. Both containers are labeled, positioned in identical environmental conditions at ambient temperature ranging between 68 and 72 degrees Fahrenheit, and the brewing process begins simultaneously. So, visual documentation starts immediately, and within the first 6 hours, some subtle differences begin emerging. The raw rice actually settles toward the bottom of the container, creating these zones where anaerobic pockets might develop, even though there's aeration going on. Now, the cooked rice, being softer and more fragmented, disperses throughout the water column more evenly. Foam development, which is an indicator of active microbial respiration, shows up within 12 hours in both treatments. But the character of this foam differs noticeably between the two batches, hinting at the distinct biological processes taking place beneath the surface. Mid-experiment check. The science unfolds. Daily monitoring reveals some fascinating patterns in the chemical and biological evolution of each tea. Temperature readings, they remain pretty stable across both treatments, just hovering around ambient conditions. But, pH values tell a much more dynamic story. The raw rice batch shows a gradual pH decline from 7.2 to 6.8 over 72 hours, and that actually indicates the production of organic acids as microorganisms slowly break down those complex starches. The cooked rice treatment, on the other hand, demonstrates a more dramatic pH shift, dropping from 7.1 to 6.3 within the same time frame. This suggests, you guessed it, more vigorous microbial activity and faster fermentation of the readily available carbohydrates. Visual changes really start to accelerate after the 48-hour mark. The raw rice tea maintains a darker, more murky appearance, with minimal foam production beyond the initial burst. Particles remain largely intact and rice grains show limited visible degradation even after 3 days of continuous aeration. In stark contrast, the cooked rice tea develops a thick, creamy foam layer that must be skimmed periodically to prevent overflow. The liquid itself takes on a lighter, more tan coloration, and the rice completely disintegrates into the solution, becoming pretty much indistinguishable from the surrounding organic matter. Microscopic examination at the 72-hour point provides the most compelling evidence of divergent microbial development. A single drop from the raw rice tea viewed under 400 times magnification reveals moderate bacterial populations, predominantly rod-shaped forms with occasional fungal hyphae visible at the edges. The cooked rice sample, examined under identical conditions, shows explosive bacterial growth with dense clusters of both rod and coccus-shaped bacteria actively moving through the field of view. Even more significant is the presence of extensive fungal networks, with branching hyphae, creating complex three-dimensional structures throughout the sample. This fungal development is critical because fungi, really excel at breaking down complex organic compounds and creating the soil aggregates that improve structure and water retention. The grand reveal, unearthing the results. After 96 hours of brewing, the sensory differences between the two teas become unmistakable. The raw rice compost tea emits a mild, earthy aroma reminiscent of the forest floor after rain, which is pleasant but not particularly intense. The cooked rice version, on the other hand, produces a stronger, more complex smell profile that combines sweet fermentation notes with deeper earthy undertones, indicating more complete decomposition and, honestly, greater diversity of metabolic processes. When strained through cheesecloth, the raw rice tea yields mostly intact grain particles and shows minimal residue buildup, while the cooked rice treatment produces virtually no solid material, having been almost completely consumed and transformed by the microbial community. Quantitative measurements support these qualitative observations. Dissolved oxygen levels, measured with a basic aquarium test kit, remain higher in the raw rice treatment at 6.2 parts per million compared to 5.1 parts per million in the cooked rice batch. This, suggests that the more intense microbial activity in the cooked rice tea consumes oxygen faster, even though there's continuous aeration. The pH stabilizes in both treatments by day 4, but the cooked rice tea settles at a lower final pH of 6.4 versus 6.9 for raw rice, indicating ongoing production of beneficial organic acids that can help solubilize nutrients in alkaline soils. The ultimate test involves application to living plants. Identical seedling trays of lettuce, radish, and bean seeds receive equivalent moisture levels, with control groups receiving plain water, and treatment groups receiving diluted compost tea at a ratio of 1 part tea to 10 parts water. Within 14 days, seedlings receiving the cooked rice compost tea demonstrate measurably superior growth metrics. Average height increases by 23% over controls compared to just 11% increase for the raw rice tea treatment. Leaf color, measured using a basic chlorophyll meter, shows deeper green readings in the cooked rice group, indicating improved nitrogen uptake and overall plant vigor. So, root development, when examined after gently washing the soil from representative samples, actually reveals more extensive lateral root formation in plants treated with cooked rice tea. This really suggests a better establishment potential when these plants are transplanted. These results, honestly, translate into pretty practical guidance for home gardeners who are looking to maximize the microbial potential of their compost tea. Cooked rice, as we've seen, clearly provides a more accessible carbon source that triggers rapid and diverse microbial proliferation, especially of those beneficial fungi that contribute to long-term soil health. The investment of energy required to cook the rice pays dividends in the form of a more potent finished product that demonstrably improves plant performance. However, timing matters tremendously. The cooked rice tea reaches peak microbial activity faster than the raw rice version, meaning it should be used within 4 to 5 days of brewing, whereas the slower developing raw rice tea may maintain viability slightly longer. The biological mechanisms driving these differences relate to substrate complexity and microbial specialization. Raw rice starches exist in crystalline structures that require specific enzymes, produced by relatively fewer microbial species, to break down the complex polysaccharides into usable sugars. This limits which organisms can participate in the initial decomposition, creating a bottleneck in microbial development. Cooked rice, having undergone gelatinization, presents starches in amorphous, hydrated forms, accessible to a much broader range of bacteria and fungi. This allows diverse microbial communities to establish quickly, creating the synergistic interactions that define a mature, balanced compost tea. Moving forward, this experiment opens doors to numerous variations worth exploring. How do different rice varieties, such as brown rice with its additional fiber and nutrient content, compare to white rice? Does the combination of cooked and raw rice create a tea that benefits from both rapid initial microbial development and sustained long-term activity? What happens when we introduce other cooked carbohydrate sources like oats, wheat, or corn into the brewing process? Each question represents an opportunity to deepen our understanding of the invisible world that sustains our gardens. If this experiment has sparked your curiosity about the microscopic universe thriving in your soil, subscribe to Crops the Natural Way for more hands-on explorations of natural growing methods that work with biology rather than against it. Share this guide with fellow gardeners who are ready to move beyond conventional approaches and embrace the science of soil life. Together we can build a community of growers who understand that the real magic in gardening happens at a scale too small to see with the naked eye, but powerful enough to transform our relationship with the earth beneath our feet.